Okay, well, we might as well get started. So we had discussed last time dynamic burning, and just sort of from a qualitative standpoint as to what happens if you have a rocket or a gun system or something like that that's burning propellant, and then the pressure suddenly changes. What happens to the burning rate? We argued that based on the either deficit or excess heat absorbed in the propellant, the burning rate can either go through a dip or an excursion where it increases, depending on whether the pressure is suddenly increased or decreased. And now this is an important process for modeling rockets or even gun systems. Because for guns, again, the pressure, the max breach pressure of a gun, a big gun that is, can be over 100,000 psi, and it gets there in very, very quickly. And so they want to make sure that this excursion that occurs when the propellant burns does not cause the gun system to blow up. And so there's been a lot of theoretical analysis on this, and I'm going to go over one in more detail. That's called the Zeldovich model. And it's a theoretical model for dynamic burning. And so what most of these models consider is basically is they look at the energy equation in the condensed phase. And so I already derived a variant of this earlier. Just here we got a heat source due to in-depth condensed phase reactions, and also there can be in-depth heating due to thermal radiation. That is, if you have, say, a laser that is being shown or that is shining on the surface, and the surface isn't perfectly black. Some of that radiation energy will basically penetrate inside of the propellant and be absorbed as and then there will be an in-depth absorption of that radiation energy rather than it just being absorbed only on the surface. And so the general analysis accounts for both of these effects. And usually when they're doing these analysis, they neglect both of these. So it's just sort of a steady heat conduction equation with basically with convection. Anyways, so you can show that at steady state conditions with no in-depth reactions or thermal radiation absorption, the steady state temperature profile turns into this. It's an assuming constant burning rate, which again makes sense. You can derive this in a fairly straightforward fashion. It's just a nice a second order separable differential equation that you can just really integrate normally. And then now when we look at transient burning, what the canonical picture that you have in mind is you have a steadily burning strand of propellant, and then you suddenly change the pressure conditions. And then you want to see what happens in the transient of when the basically when the propellant you want to make a theoretical model that can predict how the propellant behaves in the transient when as it reaches its new steady state. And then these can be used to determine what happens. Can your system take the burning rate excursion, how severe it is, and even if the propellant will burn stably or not. That is, will the burning rate just run away and go crazy? Okay, and so then what they do with the steady state temperature profile is that they're going to use this as the initial condition for solving the full transient version of, if I increase the pressure, I want to know like what's going to happen to the burning rate, and you need to start the temperature profile from a nice steadily burning propellant. And so that's where this profile comes in. And again, x minus infinity is less than x is less than 0. So basically, you're probably used to seeing a minus sign in front of this exponential. But remember, the condensed phase material, which is where this equation is derived for, goes from x between minus infinity and 0, and so it's defined to be, and so basically the exponential basically won't approach infinity. Okay. And then so basically this temperature profile is used as the initial conditions for the transient burning. And we have the boundary condition that the initial temperature of the propellant is not changed. So that's the temperature at all times at minus infinity is equal to our initial propellant temperature. And then what does change though, what does change with the pressure and the burning rate is the temperature gradient that is acting on the condensed phase side of the propellant. Okay, and so basically the boundary condition here is unchanged, but the slope, but the temperature gradient at the surface of the condensed phase is going to be a function of time, and that's a function of time due to the changing pressure conditions. And then basically what they'll do is what Zeldovich does is he came up with a very clever way of basically finding this function and then basically what you can use as the boundary condition to solve for a transient burning problem. So the question is then how do you get this term? Because aside from this, it sounds like a pretty straightforward heat conduction problem. It's just you need to know the boundary condition. So how he gets that is first, let's examine the characteristic times of the various regions of a burning propellant. And so, and I'm not going to go through this non-dimensional analysis or scaling analysis. It's similar to what you would have done in fluids 2 or convective heat transfer when either performing the scaling analysis or non-dimensionalizing the governing equations when you're deriving the boundary layer equations. It's a very similar process, and I'm not going to go through it for the interest of time. But so what they examined were characteristic times of the propellant, and there are, if you're changing the pressure, there are 4 time scales that you need to be concerned about. One is the time scale for a non-reacting condensed phase propellant. This is the time scale of the heat being soaked inside of the condensed phase in the condensed phase. And so this here is just given by the thermal diffusivity. Oops, wrong one. The thermal diffusivity of the propellant divided by the burning rate squared. And then again, that comes from a traditional dimensional analysis. Okay, and so that basically characterizes how much time the heat has to soak into the propellant before the surface is burned away. Okay, and so it has that much time to do its thing. And then there is a characteristic time for surface reaction if you have them for your propellant. And I'm not going to go through this, but that characteristic time for surface reaction is given by the universal gas constant times the surface temperature divided by the activation energy of the surface reaction. Okay, so this is for surface reaction. Okay, and then they will just call this some epsilon parameter times tau c. Okay, and then you also have a characteristic time scale for the gas phase flame, and that is given by really the same thing as the condensed phase propellant here, but except for it's the gas phase thermal diffusivity and the gas phase velocity squared. Okay, and then you can also show that these two parameters scale like this. If you factor out a tau c and do a more nasty scaling analysis. Okay, and so this would be the characteristic time it takes for the gas phase molecules to burn and do their thing. And then there is a fourth time. So those are the three characteristic times associated with the burning of the propellant itself. And then if you're changing the pressure, there is a fourth time scale that involves the sort of characteristic time for that basically for that pressure transient, and that's called tau p, and that's given by either one of two expressions depending on how that pressure is changing or how the experiment is forcing it. One would be just a change of pressure over the rate of change of pressure, and this would be some averaged rate of pressure. Or if you're sort of forcing a sort of quasi-steady frequency of pressure, then tau p would just scale with basically 1 over that frequency. It all depends on the experiment and how that's being performed. But at any rate, the take home here is that there are 4 characteristic time scales. There's a characteristic time associated with heat being soaked into the condensed phase propellant. There's a characteristic reaction time for burning on the surface of the propellant, and there is a characteristic time associated with the basically burning associated with the burning of the gas phase species, and a characteristic time associated with the rising pressure. Okay, and so based on these, there are 3 possible dynamic burning regimes, or 3 possible burning regimes, depending on how fast these things are. So one, there is steady state burning, and that is if the time scale of the pressurization is so slow, it's slower than the condensed phase time scale, it's slower than the gas phase time scale, and it's much slower than the gas phase surface, or than the surface reaction time scale. Then you can reasonably conclude that even during the pressure change, the burning will be steady at all conditions. So basically, if you want to understand what happens in that case, if it's steadily burning and I change the pressure, what will happen for the burning rate is it will basically just do that. Because this dp dt here is so slow that at any instant of time, the propellant is burning under steady conditions. Okay, and so that is that condition. So that one should be fairly intuitive. There is a second case called quasi-steady burning, and this in this case here, the characteristic burning time, or the characteristic rate of pressurization is on par with the characteristic time in the propellant, or it's still greater than, but it's not much greater than. The characteristic sort of pressurization time is still greater than the characteristic surface reaction time, and the characteristic pressurization time is still, oops, gotta change this to black, is still much greater than the gas phase pressure time. So basically what this means is that with this analysis here is that we can no longer assume that the pressurization time is much slower than basically how fast the temperature profile in the condensed phase propellant can respond. So we can no longer assume that the burning conditions in the propellant itself are steady. However, the gas phase, the thermal profile in the gas phase tends to respond much more fast to perturbations than the condensed phase side. You can think of it as basically this expression here as alpha G A, that's going to be smaller for a gas than it is for a solid. And also due to conservation of mass, if you're changing the density, if the propellant density is on the order of 1,600 kilograms per cubic meter, and the gas phase density is on the order of 10 kilograms per cubic meter, or 1 kilogram per cubic meter, or 100. At any rate, the gas phase velocity will be much higher than that of the burning rate of the propellant on the condensed phase side, and you're squaring that. So this is going to be a smaller number divided by a larger number. So basically, you expect that the characteristic time of the gas is going to be less than that of the condensed phase propellant. So there are these conditions called quasi-steady, where you expect that the transient effects will be important for the propellant, but they won't be important for the gas, just because the gas can respond so fast. So basically what we are assuming here is that the gas phase flame itself at any pressure condition is steady, but the condensed phase temperature profile is not steady. And so here you can say that the pressure change is moderately fast. In most rockets and gun systems, this is the regime of dynamic burning that you are interested in. And then there are truly unsteady burning conditions where the characteristic pressurization rate is on par with all 3 time scales. And then basically both the condensed phase propellant and the gas phase are all unsteady. There is no basic theory that I know of for truly unsteady burning. And they require, because the gas phase responds so fast, they require very rapid pressure changes. I can only think of one application where you would need to worry about this. It was just a blurb in a call for proposals about a year ago, and that was they were interested in a device where you have a propellant and you send a detonation wave, a gas phase detonation wave, across the surface of the propellant without detonating the propellant. And that's all I'm going to talk about that. And so in that case, as the gas phase detonation wave would sweep over the surface of the propellant, you would have an extremely fast change of pressure. And in that condition, you would almost certainly be transient in the gas and the condensed phase propellant. And the other condition, in the other case, you'd be worried about something like that would be if there is something really bad happening to a rocket motor and you want to study what happens as it's blowing up. But again, they haven't studied these things very much because the application of it was just a thought that occurred maybe a few years ago. And they're not interested in that case where you have a rocket motor that's in the process of blowing up just because it's already a lost cause. And so they're not interested in, so they haven't been interested in that very much. But anyways, so this regime here, scientifically to me, it'd be by far the most interesting regime, but there's only a few practical applications for it, so it's simply just not well studied. Although, again, that may change depending on how that idea pans out.
Would you consider chuffing in that quasi-steady regime where the pressure is kind of frequently, it's got this frequency associated with it?
Yes, even chuffing is in this regime here. Again, because the changing timescales here needs to be very fast, just because the gas phase timescales are so fast. Okay, because again, you would again, with the exception of the solid propellant detonation engine, you would never consider designing a rocket or a gun system to be in this regime here. You would, well, you nominally design them to live here, and you consider transient and off-design sort of cases to live here. Typically, if you're here, that means you are in the process of basically destroying your gun or your rocket. And again, it is only recent with the solid propellant rotating detonation engine concept that you would even need to consider these unsteady, basically this unsteady regime for a practical condition. But that concept is a little bit nutty. I don't know if it will pan out. I don't know if the dark zone is even thick enough to support a gas phase detonation. If it works, great. If not, kind of oh well. But at any rate, so the theories of dynamic burning only really consider this regime here. I suspect that in this regime here, if you want to study it, it's going to require full simulations, a full transient multidimensional simulations, and extremely careful experimental diagnostics. I don't think there are going to be any simplified theories for basically this regime here, just due to how dynamic it would be. Okay, yeah, even turbulence, you would not need to, even a turbulent burning, crazy erosive burning scenario, you would probably not wind up in this regime here. Okay, anyways, unless something happens that slows the gas phase process, the gas phase combustion down, yeah, I don't know. Again, I can't think offhand of any normal design scenarios where you wind up in this regime here. Okay, are there any other questions? Okay, so in the quasi-steady regime, without in-depth condensed phase chemical reactions and in-depth absorption of thermal radiation, Zeldovich, again, he's a famous Russian, actually self-taught. He didn't do any formal schooling. Self-taught astrophysicist and combustion scientist. He's almost more famous in astrophysics than he is in combustion. But if you work in explosions and detonations and fast flames and Chapman-Jagay deflagrations and things like that, the equations that we solve to do those types of simulations are very similar to the equations that are solved by astrophysicists to study supernovas. Because after all, a supernova is just the detonation of a star. And instead of chemical reactions, you have thermonuclear reactions, but the equations themselves are almost the same. And so there's a lot of commonalities between the stuff we're studying now, especially when we get to the multi-phase aspect of it, and gas phase detonations to astrophysics. So a lot of the old scientists who developed the sort of combustion theory, they basically worked in both astrophysics and combustion theory because, again, they are very close to one another. Just don't tell the astrophysicists that. And I have a goof up. Let me fix this. So Zeldovich proposed that we solve this equation here that I'm correcting. That we just have, again, this is just the transient heat conduction equation for the solid propellant region, without any in-depth condensed phase or heating effects from condensed phase chemical reactions or thermal radiation absorption in depth. Okay, he just assumed that the temperature far away from the propellant surface is at some initial temperature that is unchanged. And then he also assumed that the temperature gradient on the condensed phase side of the propellant is given by some function of the burning rate and the pressure. And he argued that this term here is equal to RB over the thermal diffusivity times the difference between the surface temperature and the initial temperature at steady conditions. And so this here, basically going from here to here, appears to be quite a leap. So where does this come from? Well, to be honest, we already derived this relationship. And so recall when we were analyzing the burning rate of the propellant using our sort of really simplified phenomenological model, that if we turn off the condensed phase reactions and in-depth radiation, we had this expression where we said that on the condensed phase side of the propellant, the conduction heat flux going into the propellant is equal to the density of the propellant times the specific heat times the burning rate times the difference between the surface temperature and the initial temperature of the propellant. So essentially, this is saying that the conduction heat flux going into the propellant at the surface is equal to the sort of change of enthalpy between the propellant from the propellant at its initial temperature to the surface temperature. That's basically all that's saying. So it's just a really nice energy balance. And so what we can do here is this here is our phi CS. So we basically solve for phi CS. And so we just, we basically solve for this. We have RB times our difference in temperature. And so we have this, and notice that these are the same up here. So, check. And then we have basically rho, we have rho Cp over lambda P, and that's the thermal diffusivity. And so then we wind up with this expression here, and this is just phi CS. And so we've already derived this expression here. Oops, wrong one. We've already derived this expression here. So, and so while it looks kind of strange, but it did come from a very formal condensed phase energy balance. Again, if you're assuming constant density, constant specific heat, and constant thermal conductivity. Okay, so are there any questions with that? Okay, and so what Zeldovich argued is that if we are is that basically this temperature gradient at the surface, at the condensed phase side, is going to be dictated by what's going on the gas phase side of the interface. And so if we assume that the gas phase is that the gas phase can respond so fast that essentially the sort of gas phase can respond that the gas phase can sort of respond instantly, what Zeldovich argued was that instead of using the instantaneous phi CS, which you need to know the instantaneous surface temperature, the instantaneous burning rate, and that's what you're trying to find. So that becomes complicated. So what Zeldovich basically argued that if you are in the quasi-steady burning regime, you can use phi CS based on the steady state operating conditions based on the pressure of your current based on the conditions that your propellant is basically currently burning in. So basically, rather than using the instantaneous values of the burning rate and T naught and basically TS naught to basically find this heat flux, you basically just look at the pressure and you say, okay, well, if the pressure is this value here, I can look at Saint Robert's law and get this number here, and I can look at a different pyrolysis law to get the surface temperature, and I can also get a basically T naught term here from a different relationship, and so I'll discuss how those are obtained. Okay, so basically he assumed that if you're in the quasi-steady burning regime, you can base phi CS or the condensed phase temperature gradient only on the steady state operating, only on the steady state burning rate and and the pressure at basically which the propellant is burning at that instant of time. And so how do we get TS naught? Well, again, Zeldovich's approach requires either detailed numerical modeling, which didn't exist when he derived that in like the 1940s. But what they could do is do some experiments. And so the Zeldovich approach is a nice way to study dynamic burning based on experimental data and some really light numerical modeling. I mean, the numerical modeling was light enough that they could do it in the 1940s. So TS, there are different ways of finding TS naught given an RB. And these are called Zenon's pyrolysis law is a very common way of doing that. For those of you working on the variation of project 2 that involves studying the double base propellant, you will be using a Zenon's pyrolysis law to relate the surface temperature of the propellant to the steady state burning rate. Okay, and so what Zenon's pyrolysis law, what Zenon proposed was that the burning rate or the burning rate mass flux, they are just the burning rate and the burning mass flux are related to each other just by the propellant density, which is a constant. And so just pay attention to which form that is in if you do look these up. And you can convert from one form to the other form by just multiplying or dividing A by the propellant density. But anyway, so what he proposed was just a really simple Arrhenius form based on the surface temperature. Okay, and again, as was stated, I think last week, is that yes, the higher the surface temperature is for the same propellant, the faster it will burn. Okay, but okay, and so but that's for within the same propellant. So for a given propellant, you would need to measure A and that activation temperature for the surface pyrolysis. Now, this is not a surface reaction. This is just a sort of bulk global surface or a bulk global pyrolysis law that basically you could think of it as a reaction that goes from propellant and that goes to pyrolysis products. Okay, and so that's basically all that is, stating. And then there are some experiments for JA2 where, and so basically this or other pyrolysis laws can be used to relate the steady burning rate to the steady value of the surface temperature. So that links these two parameters right here. And now we need a link to the sort of steady to a steady T naught. And you can use the definition of the temperature sensitivity of the propellant to do that, where you can basically link up RB naught is AP to the N times this temperature sensitivity effect here, and then you can relate a T naught to all of the other parameters. Okay, and so then if you have all these parameters, then you basically then have phi CS naught. And then you can basically know you basically know your condensed phase heat flux as a function of pressure and the steady burning rate at that pressure. Okay, and so then essentially you then combine the Zenon pyrolysis law and the temperature sensitivity to basically produce our desired function. Okay, and so and the other way that is also done for JA2 is that you can also correlate TS equals what is it for Ts equals some function of P and T naught. Okay, and then for JA2, this is actually a known function. It's been determined empirically, and it's for JA2, it's equal to Ts is equal to, let's see, A1 plus A2 times T naught plus B1 plus B2 times T naught times P. Okay, and so for JA2, you can use either this or this. This function here is the more desirable one to use if you have it, but you don't always have it. In fact, I helped Bauchi do the experiments where he was making this correlation. I was just the grunt because the office where I was doing my computations was just right next to the test cell where he was doing this work. So I got roped into doing a lot of the grunt work on this. But basically, he determined this map, and he found sigma p from this. So for JA2, this relationship here and the sigma p relationship that I showed earlier, they are all internally consistent. Okay, but anyways, so and basically there are multiple ways of doing that. If you know the temperature sensitivity function, you can use it this way, or if you have measurements and you measure the surface temperature of the propellant at a bunch of different propellant initial temperatures and pressures, you can fit a function to that surface, and then use that. Okay, and then again, these can be combined to find our desired heat flux as a function of the burning rate, pressure, and any other conditions at steady operating conditions. Okay, then the transient energy equation is solved using this temperature boundary condition based on the propellant burning rate and P naught, and the initial condition is the steady state temperature profile. Okay, now there is one gotcha here when you solve this, is that technically the RB here is not constant. That's changing, so there is a little bit of an at each time step. If you were to solve this numerically, there is a little bit of an iteration that you basically have to do because you don't know that burning rate, and so that burning rate would be a function of the surface temperature or your pyrolysis law. So you need to go back and forth and basically iterate at each time step. Okay. But again, but it's an iteration that I'm pretty sure converges pretty quickly. Because again, they were doing this analysis in Russia in the 1950s and 60s when they didn't have much for computers back then, especially in Russia. Russia, they tend to be much better with the mathematics than we are. And we focused a lot more on the computer analysis. Okay, so anyways, so then you got your thermal, or you got your temperature gradient boundary condition. Assuming again we are in the quasi-steady burning regime, where we assume the condensed phase heat flux is basically being produced, is basically being imposed by the gas phase flame, which is responding essentially instantly to the changes in the pressure. And so basically we only need to look at that heat flux as a function of the steady burning conditions at that temperature profile. Again, it's a bit of an assumption that Zeldovich made, but it seems to work fairly well for the quasi-steady burning regime. And if you wanted to use this approach for the unsteady burning regime, you could not do this step right here. It would have to be phi CS basically without the naught. So it would have to be an instantaneous phi C naught, which would mean you would need to fully couple, do a full detailed calculation of the gas phase flame to a full detailed calculation of the condensed phase zone. and basically solve them together in lockstep. Is basically what you would have to do in the unsteady regime. All these sort of theoretical and sort of mathematical simplifications that Zeldovich made to make it solvable back then, those would not be in play for that kind of condition. But again, for the conditions they were looking at, that is not a big deal. Okay, but anyways, basically what they did for JA2 back in 2006. These are the experiments that I helped out with. I didn't help out with the computations, but what basically what Bauchi-Zhang did was he then took his correlations that he deduced and then looked at the burning of JA2, which is a double base propellant, and just looked at the effect of basically various rates of pressurization. And this basically here is the deviation from the steady burning rate at the higher pressure. And just notice that the Zeldovich model does predict this little this basically little spike. And in some conditions, it's actually very dynamic. You get these little spikes up, then sort of an oscillation, and then back down. I don't know if that's a numerical effect or if that's just due to other things. Okay, and so the Zeldovich model is a fairly accurate and fairly straightforward way. It seems confusing, but after you do it once or twice, it's not that bad. Okay, and now there's an even simpler approach, but its regime where it is applicable is much more limited, and that's called a so-called DP-DT approach. And really what this is derived is by doing a perturbation analysis or an asymptotic analysis for the condensed phase propellant. And they basically assume a small change in pressure. So to do this so-called DPD approach is that the change of pressure needs to be small or fairly slow, or small and slow. Okay, and so what they do is they assume that the burning rate is a function, is given by this function here, where it's some RB naught, which is a steady part, plus some constant times dp dt. And they basically do a perturbation analysis. They substitute this in, do an asymptotic analysis, and basically assume that that's small, expand about that, and then do the analysis. And then Cryer in 1972 derived this expression here, or he derived this expression here, where RB is RB naught times the quantity 1 plus some psi times n, which is our burning rate exponent, times the thermal diffusivity of the condensed phase propellant, P, divided by the pressure times the steady burning rate squared, and then times our pressurization rate. And the psi is a material constant of the propellant, and psi is given by this expression here. And his expression was basically generalized enough to account for a surface reaction if your propellant has one. If it doesn't have one, then this term here is 0. Okay, and again, where n is the burning rate exponent for St. Robert's law, and kT is an exponent that comes from a simplified pyrolysis law, where basically the burning rate, I should say RB naught, is equal to some constant B times the difference between the surface temperature and the initial temperature raised to the power kT. And this is just a different functional form. Recall that for Zenon, we had that Zenon proposed an Arrhenius law. So if you know a Zenon pyrolysis law, you can basically locally refit it to this functional form here. Find your B, find your KT, and find your local TI, and then basically refit it, and then find KT, and then you can find your psi, and then basically then you have everything in terms of propellant properties, and then you can just find the response of the propellant just based on the change of chamber pressure in your rocket or your experiment or the gun system or something like that. Okay, and so this analysis here is much more limited. You can only use it for small pressure changes, but it is nice. You don't need to solve the heat conduction equation that was sort of ruled out, or that sort of disappeared in his perturbation analysis. And so this expression here is simple to use in the sense that it is explicit. There is no there's no heat conduction equation to solve. There's no Zeldovich sort of parameters and correlations that you need to do. And so this here is a decent first cut, but it starts to fall apart if dP dt is high, or the change of pressure from the initial pressure is also high. It starts to fall apart. Okay, and so you do need to be careful using that one, but it is easy to use. And then, just for historical purposes, there have been a lot of researchers who derived essentially this exact same expression here, except for they found that psi was basically constants. And for instance, von Elb found that psi was equal to 2 based on his assumptions for his perturbation analysis. Sommerfeld and Cryer found that that constant was 1/2. And then Paul, Levine, and Flong found that constant was 1. And basically, these were just these different values, or this disagreement in what psi was based mainly on the assumptions that they made in their analysis. And I would need to look in the papers to understand the details of their analysis to understand why these constants are kind of all over the place. But basically what Cryer did, I believe this was his PhD, I believe this was Cryer's PhD work. Basically, he did a more detailed analysis, didn't put as many assumptions into it, and found this functional form here. And I believe this, at least in part, explains these different parameters. Okay, and so basically, this expression here is a bit more general. So I would recommend you use this one, unless you don't know KT, and then you're forced to use one of these. Okay, and so that is it for today. Are there any questions on dynamic burning? Okay, yeah, it's just something to be aware of. It gets very complicated. In the most extreme case, you have to consider full transient simulations of both the condensed phase propellant and the gas phase flame zone. But luckily, numerical techniques with these days, if there's ever interest to doing that, those are definitely simulations that are doable basically these days, because it's not the 1940s.